Okay, folks, just as a reminder, we're going to be continuing our practice of holding the team meetings at the end of this class, for the final 10 minutes or so. So I'm going to get started right now so we can complete the material prior to that. Okay, so today's lecture builds on the lecture I gave remotely, unfortunately, last week, which focused on estimation. Today's lecture deals with scheduling. Scheduling has a close conceptual relationship to estimation. Estimates often give us a length of task duration or effort. So when we have a task that has some contiguity to it, in other words, it's pretty much straightforward thing that has to be done after one after the other after the other. We can use estimates to give us a sense of how long that task will take. But if you just were to take the duration of the various tasks that you have to undertake, say for an incremental deliverable, and just total them up, you're going to be fooling yourself if you think that's how long in calendar duration it's going to require. Why is that? So suppose that we had a set of tasks that need to be undertaken to complete incremental deliverable 2. And we could list them out. We could put durations on them. Suppose that we'll estimate the durations in hours rather than in jelly beans or unicorns. So suppose we have 4 hours for this one, 2 hours for this one, 1 hour for this one, and 4 hours for this one. If I were to say, well, okay, we can complete that deliverable, that incremental deliverable 2, within 11 hours, 4 plus 2 plus 1 plus 4, would that be accurate? Why not? What is it missing? Okay, so it's missing the fact that one task might have to be done for another, after or before another. So these tasks might have to be done in an order like this, in which case it would take 11 hours of calendar time. On the other hand, it could be that they're all more or less independent. They could be done in parallel with enough resources. So one person could undertake each of the tasks, and maybe it would complete in 4 hours. 4 because the maximum of all these tasks requires is 4 hours. Scheduling helps us go from task durations and dependencies on the one hand to descriptions of when we need to finish a task to finish the entire project in time, for example, within some defined time that you'd like to finish it in. And what should we do before what? What things can be done in parallel, etc. So scheduling allows turning many task durations into an estimate of project length. What's the minimum time we could finish this? What's the earliest time we could start a given task? And what's the latest time we have to start it if we're going to finish the entire project on time or not add to the length of the project? Now, it turns out this is important not just for time, but because of money. Has anyone here taken courses over in commerce or courses on microeconomics where you've been exposed to the time value of money, discounted cash flow, net present value? Okay, good. So you folks will have an appreciation for the fact that, as sometimes people put it in a very pithy way, time is money. Delaying something can have consequences. Delaying cash flow can have very material consequences in terms of opportunities foregone, in terms of potential sources of money that could have come about that are ruled out because of the delay. Delays cost things. There's giant court cases about who's responsible for the delay of a project, for example. This isn't as common in software as it is in some other industries. So if you go to construction, you go to large-scale engineering projects like construction of ships or construction of airplanes, you will get into an area where litigation is unfortunately all too common. So time, matters for money as well. So why schedule? Well, there's a variety of reasons here. It lowers the chance of a delay, and if a delay is going to occur, it helps in recovering from it. We'll introduce today the important notion of a critical path. And this is a very, very important notion. It's one of the most testable notions in this class, and I certainly expect everyone here to have a grasp of it. It will consist of a sequence of activities. Typically there's one sequence. Occasionally you find more than one, but typically it's one, which if you don't stay on top of them, if you don't execute them one after the other as quickly as you can, you'll unnecessarily delay the project. By contrast with that, there's going to be a set of activities that are not on the critical path, a set of tasks where you have more slack. I'll actually introduce that synonym for what we call float in a technical sense, to mean activities where we have some latitude for when we're going to start them. We have some give. You can use different terms to describe it. We don't have to start it by the earliest possible time we can start it. Instead, there's some latitude there. So we'll see that not all tasks are the same in terms of this. Some tasks we have to really keep our eye on, keep the eye on the ball for these tasks, while other tasks we can afford to be a little bit looser with how quickly we attempt them. That's really A1 important. In past projects within this class, I found it really, really helpful to identify what that critical path is up front. What are the things that need to be done one after the other without miss for us to deliver this thing as quickly as we can? That will help you marshal your effort. Okay. Unfortunately, delays often result from poor planning. There's necessary delays sometimes, but there's a lot of delays which come from sloppiness, come from inattention to the critical path. And those delays can be eliminated through careful scheduling. Turns out that scheduling in larger projects can also require just assistance in bookkeeping and reasoning about the huge number of details involved. So there are projects out there with thousands of tasks. This is less common in software, which has embraced a much more incremental model, which sort of largely decouples the scheduling for one incremental deliverable from the scheduling for the next. This is really important. But even so, there's often projects which span multiple sort of meta projects that span multiple projects. An example would be suites of products. So you look at something like Star Office, or you look at something like Microsoft Office, which spans multiple products. They need to keep track of a lot of details about the incremental delivery of these projects. Turns out that resources can be difficult to manage. This is less of a problem in software than in some other areas. In construction, you have all sorts of resources. You have dozers, and you have trucks of various sorts, and you have certain types of other earth-moving equipment. You have generators, all sorts of things. In software, we have resources too. They aren't quite as fun to look at, perhaps, but they're important. So what resources would we have in software that might constrain whether a task can be delivered on or not? That availability of that resource is critical to deliver on a task. People is the most critical. Yeah. Far and away the most important resource in software engineering. What's another resource, though, that might sometimes be required? Okay, yes, absolutely. So if you have a farm of test machines, for example, that you want to hit during your tests, you might need a whole set of VMs established. Sometimes even physical machines, depending on the nature of the work being done. In some cases, in some projects, there might be hardware debuggers. Those with computer engineering background may have seen logic analyzers before, which for hybrid sort of systems, maybe developing firmware for a project, you need to make use of these resources. And it turns out that formalization here is really necessary for effective delivery on a lot of projects. But importantly, it's not sufficient for managing. We're dealing here, ladies and gentlemen, with abstractions. We're dealing with a simplified representation of the schedule, which allows us to reason about a lot of things, but hides a lot of details. And often, those details matter. They matter because they could stick up and bite us in other domains that we haven't captured with the schedule. So what we'll be talking about today is not a silver bullet for scheduling, but it can help a lot, and particularly this whole issue of identifying the critical path. Okay, okay, I think I'm going to sort of leave that. Often left unsaid in these sort of lectures is, what shouldn't we schedule? Well, scheduling is so great. Why not? Schedule everything. Choreograph everything down to the microsecond at which it's going to obtain. Well, it turns out that it's overhead associated with it. Interpreting the schedule, communicating it, readjusting the schedule when things fall off of it. And this can require effort. It requires effort on the part of project managers or others who are involved in scheduling. So typically we don't schedule really minor activities. In most situations, for example, when we have a resource, such as an elevator in a building, we don't schedule, at what time the elevator will be on a certain floor. That's dynamic. Depends on the vagaries of who requests it, etc. Now, if we have a construction project going on in a building which requires very intricate movement of materials up and down throughout various floors, and there's very well understood sort of staging about when things have to be available, we might actually schedule an elevator. But sometimes uncertainty is just too great about activities and their timing and duration. For example, the time we'll find particular defects. How many defects will be found? What particular developer will be ready at a given time to take on a given feature? What tester will be ready to do, create a new test? So in these cases, we don't try to schedule it. We try to keep our schedule to higher level important activities. So it's important to recognize that scheduling is not used universally. We do a lot of dynamic scheduling, and that's all fine and good. We dynamically coordinate flexibility. And this is very common in software as well. Task queues for coding. Who does what feature, etc. So, ladies and gentlemen, we're going to talk today about two basic mechanisms for describing scheduling. The first is depicted on the screen right now, and that's Gantt charts. You will see Gantt charts in countless domains of human activity, and they cross disciplinary domains very readily. They're one of the most common ways of characterizing visually how a project will take place over time. Okay. And they're very straightforward to read. So we might have, for example, a set of activities running down here, traditionally on the y-axis. And then we have a set of an axis associated with time running horizontally, which might be numbered relative to the kickoff of the project, to the start of the project. And we'll depict, using a bar, the time in which a given activity is active. Okay? So, for example, here we have some preparation of activity schedules within the first 2 weeks. Other types of activities, typing and editing, are available so later in the schedule, etc. Some activities are so short they're almost events. For example, submission of certain types of data, and we may just show them with a marker. So this is a Gantt chart. It depicts, for a given set of activities, the durations of that activity and during what period of time that activity will be active. How many people have seen Gantt charts before here? Okay, yeah. So very, very, very common. By contrast, we're gonna compare this with CPM networks, critical path method. Gantt charts are much older in their origin. They actually came about less than a century ago, rather surprising given how ubiquitous they are, in World War I. They were actually used in planning, for example, munitions, creation of ammunition, bombs, and those sort of things for World War I. And they're a very effective communication tool. They're very popular for representation of simpler schedules. And it turns out we can do them hierarchically, which is kind of interesting. The key shortcoming of Gantt charts, despite their popularity, the key shortcoming is they don't depict dependencies. So there's no dependency shown of what depends on what. Now, why is that important?
Actually, they do. The reason is because when we find all these icons,
Okay.
yes, we can show dependencies.
Well, you can. Okay, classically they don't. It's true that in Microsoft Project and Primavera Project Planner, you can draw lines between these that will essentially characterize dependencies. But classically, if you look back, many decades, they have not depicted dependencies. In their pure form, they don't. That's a hybrid representation. I know because I've worked with those project planners before, and you can augment them with dependency information, but in their pure form, Gantt charts do not depict dependency. However, this is a major shortcoming because we often do want dependencies, and so they've been augmented. And so you get these hybrid forms of the sort that you're describing. Okay, so the key shortcoming here is of importance for what reason? Can anyone help me understand why are dependencies so important? Why have they introduced them in these sort of hybrid forms? Why would we want our Gantt chart to have information on dependencies?
Directly related to time.
Okay, it's related to time, but it's related to something else that's a very practical need during projects. Under what situations would we need dependencies? Okay, and why is that so important, particularly in the midst of the sort of the hurly-burly of projects executed? Okay, I'm going to play devil's advocate, though. I mean, if I just adhere to the schedule, if I say, okay, I'm going to look at this Gantt chart, and I'm going to start this in week 1, I'm going to start this in week 3, I'm going to start this one in week 6. Why do I need to know what depends on what? I can just mechanically execute these things.
What if we suppose we need to change the Gantt chart?
This is the main issue. It's an issue of change. It's an issue of managing change. And ladies and gentlemen, if you really think about a lot of the principles that we're talking about in this course, a lot of them have to do with managing change. You could argue that risk management is a lot about managing change, buffering yourself from change of unexpected sorts. You could argue that model view controller mechanisms that we've mentioned are about managing change effectively. For example, the fact that the UI often evolves faster than the underlying model, the underlying business logic, the underlying, in fact, the database representation. We could argue that some of the techniques like inversion of control is about managing change, so that we can go change a config file as to, for example, what information we want logged, or we could change it as to what components we want to be within our system for easy mocking and so on, in part because we want to be able to change things quickly. Well, it turns out that the dependencies are key to managing change when it comes to schedules. And this is one of the reasons why Primavera Project Planner, Microsoft Office, and other tools have worked to incorporate dependencies not only in CPM diagrams, but they have created these hybrid schemes that were mentioned. Gantt charts are traditionally used as a preferred reporting format, as a preferred format for displaying information about what will take place when. When we work with these sort of schedules directly, generally we try to depict project components, project tasks, in a way that puts front and center the dependencies among these things. And we're going to be dealing with a simplified representation of this in this class, which builds on what's called the critical path method, but hides certain details that are important for practical use. So for someone, for example, who's worked on projects in the past, you may have used multiple types of dependencies. For example, a start to start, start to finish, finish to start, finish to finish types of dependencies, which are actually have their logic associated with them and can capture a variety of rich situations. We're going to deal with the simplest and earliest form of dependency, which is a so-called finish-start dependency. It's a dependency where activity A has to finish before activity B can be started. Okay. And it turns out that you can elaborate the other types of activities so that they can kind of end up using this if required. Okay, let's talk about the critical path method. The critical path method, in contrast to Gantt charts, which originated around World War I, to the First World War, critical path method postdated the Second World War. They originated at DuPont Corporation, and they're sometimes done in a more narrow way, but they basically depend on a directed acyclic graph, what we call a DAG in computer science. DAGs are your friends. You'll see them in many areas of computer science, compiler theory, for example, planning, etc. And one of the features of DAGs is they can be topologically sorted. What do I mean by topologically sorted? Can anyone say here?
There's a strict ordering of the vertices such that the paths always go. So the path basically all point in the same direction.
Yes. So we can characterize the ordering of activities. It's a partial ordering. It's not a full ordering. It's a partial ordering, but such that those activities, if A depends on B, then B occurs in our listing for A. Okay. But it may not be a full ordering. If we have activity, for example, if we have these as our activities, we might have, and let's call this A, let's call this B, let's call this C. We might have A going, and then B and C going in parallel with one another because there's no dependencies between B and C. Okay. So it's a partial ordering. It's not a full ordering, which would require ABC or ACB to be specified. Here, what we're doing is we're specifying activities and associated information, most notably duration and dependencies, and we're going to run a scheduling algorithm that will schedule those activities over time for us. They'll tell us when things have to start. Okay. So this is a sort of depiction of a classical Gantt chart showing activities in their periods when they're active. So let's talk about the critical path method and its components. In its simplest form, we basically define activities from some task list, and for each of them, we estimate the duration of that activity. We estimate how long that activity will take, and we can choose our units: days, hours, weeks, what have you. Now, if you use tools like Project or Primavera, Project Planner, and there's no shortage of other tools out there, you can additionally typically specify resources, most notably dollars, potentially other resources, testing machines, or what have you, hardware debuggers that will be required for a given activity. And it turns out this is important. We're going to gloss over this. In this class, I used to do a couple lectures on this and talk about how you handle resource-aware scheduling so that you make sure, for example, you never require within your schedule more than n test machines to be in use. That is, you define a schedule, you seek a schedule which fits within certain resource constraints. And it turns out there's some very interesting algorithms and challenges there. And one of the big ones is that some of the naive algorithms, well, the naive algorithms are what's called NP-complete. What does NP-complete mean? Anyone tell me? What is NP-completeness? Okay, so it's actually not quite that. It's related to this notion of polynomial time, but it turns out that there's a this has to do with the so-called complexity of algorithms, and more generally, how much time it requires to solve certain types of problems. So if you ask me a problem, what's the fastest way to go via plane from Saskatoon to Washington, D.C.? There's algorithms that will search out the answers to that. And generally, we're going to have some input. Maybe it's information on what flights go to what airports between major cities in North America, or what have you. And then there'll be some output. And we can classify algorithms for how long they require as a function of the input. We use this, you've probably seen theta of n notation, O of n notation, and omega of n notation, which would try to quantify, give us bounds, yes, and they vary how tight their approximation is. It turns out that there's a whole class of problems, ladies and gentlemen, which we don't know how to solve efficiently. Based on the input size, the best known methods for solving them on a deterministic machine require exponential time, a time that is exponential in the size of the input. Now, exponential time is unfavorable in terms of its demands. If we add to the input size, say 1 add to the input size, the amount of time goes up multiplicatively, so it might go up by a factor of 2. That is not good. You add one more list to your, one more to your list of airports or something. If that doubles the amount of time it takes, very quickly you're going to have too many to really reason about. Now, it turns out that this large class of problems, though, interestingly, if we could do things in a parallel way, it may be that we could do all of these in polynomial time. We could do them instead of exponential. We could do them within polynomial time. And there's a large class of problems which are what's called NP-complete. So any one problem can be mapped into another problem and then solved within polynomial time if we had the ability to do things in a non-deterministic fashion. And it turns out scheduling is one of those things. So there's a whole class of problems which, if we could solve scheduling, if we had some way of solving it, for example, in polynomial time using some sort of fancy quantum computer or something like that, we could then solve a whole bunch of other problems at the same time. Okay, so this is class of problems called NP-complete problems, non-deterministic polynomial time problems, which, if we could solve one within polynomial time due to some, incredible advance, then it would allow us to solve them all. And there's a very important question of, does NP equals P, which is a big unsolved problem. Does what's solvable in polynomial time equals what's solvable in non-deterministic polynomial time? In any case, it turns out scheduling based on resource constraints is tough. We're going to abstract over that. We're going to be dealing here with scheduling based only on considerations of duration, what are the activities, and what are the dependencies between the activities. And we're going to have an algorithm which you turn the crank, and it's going to, within a very efficient way, linear time in the input, give us recommendations on the recommendations. It's going to give us clear statements on what's the earliest time we can start an activity, what's the latest time we can, the earliest time we can finish it, what's the latest time we can start it without delaying the whole project, and what's the latest time we can finish it without delaying the whole project. Okay. So an important note here is that the relationship, the dependencies between activities that we're describing here, these dependencies between activities, will be describing constraints. about which activities must be finished before which other activities can be started. Okay? And these relationships, these dependencies between activities reflect constraints. These reflect constraints that may be managerial in character, that may be based on resources. We only have so many developers to do tasks. They may be regulatory in nature, that by law you have to finish this, you have to get a bid package assembled before you can put it out for bid, or certain types of ethical permission has to be obtained before you can proceed, certain types of environmental approvals or what have you. Or it may be physical in nature, that you can only fit one thing at a time in some constraint. We're going to use a technique that's called activity on node representation, okay? And without going into all the details, it turns out this is related to a technique known as precedence diagram method, which is one variant of CPM, or bubble diagram method. This is the most popular one in software, so if you use Project or use any number of other projects out there, or packages out there, this is the most common one. And this algorithm is going to give us, given the tasks, and given the dependencies, the task durations, we're going to compute what these ones here. Earliest start time, latest start time, earliest finish times, and latest finish time. We're going to gloss over the fact that in these packages there's a variety of other types of dependencies. So this is sort of a crude little example I adapted, but suppose we had some activities shown here in boxes, and then the dependencies from activity A to activity B indicate that, for example, the help system has to be finished before integration across the entire project should take place. Or developer A has to finish their work before it can be tested, or what have you. Have to finish their development. Okay, it turns out there's another representation called activity on arrow, which used to be more popular, but it has a set of constraints that you don't have to worry about. I want to focus here on CPM algorithm. Okay, so the input to it again is task durations and dependencies, and that includes discussion of what each task is. Okay, and it derives these early and late finish and start times for each node, and it's linear. It's linear in the cone tasks, okay, which is sort of the natural way of specifying the input. Now, I want to drive home a point here. This is one of the most testable things in the whole course, too. Critical path method is coming up, and that can be highly testable. But this is one of the most testable, one of the most quizzable. It's the definition of early start and early finish. That's what the algorithm is going to be figuring out for us. Early start, early finish, late start, late finish. The early variants of them, students sometimes get confused about this, so I want to be clear about this. When we say early start and early finish, we're talking about the earliest time that we can start or finish. No, we can start, say early start, the earliest time we can start a given task, given all the other things that it depends on. That is, all the things have to finish before it. Again, we're not going to deal with start to start and finish to start, or excuse me, start to finish type of dependencies. We're dealing only with finish to start dependencies. So early start is earliest we can start a given task, given the things that have to be finished before. Okay? Things that have to be completed before. Now, some of those things will be described as things that directly depends on. So it, for example, we may be dealing with B, and that depends on A. But it could be that before A, there's something Z that A depends on, and B's earliest start time is going to be affected by the early start time of Z. Okay? By contrast, so students normally have no problem with this. And we'll go through some examples. Okay? Go through a common sense example. By contrast, late start and late finish. This is the one that often trips students up. Late start and late finish. Let's talk late start. It's the latest we could start a given task without delaying the project. Without unnecessarily delaying the project is what you have to think about. So the project can finish by a certain time according to early start, early finish. And that will induce, that will imply, that will require us start a given task within a certain window of time, or else we'll push the project unnecessarily late. Now, it turns out that project management software allows you to impose external deadlines on a given project. Like, what's the latest this project could finish? Here we're just going to deal with, for simplicity, deal with situations where the finish of the whole project is defined using the early finish associated with given nodes within the project, and we'll see that in a bit. Okay, so here we have early start, early finish, late finish. Those are the primary things that the algorithm is going to compute. And we can depict these in various ways. In various software, we'll use different diagrammatic representations. You'll notice they're depicted here in hexagons, etc. We're going to go through a little example here, or they'll be filled in here. Early start, early finish, late start, late finish. Okay. But first, I want to develop some intuition. The algorithm is going to consist of two passes. It's going to be a forward pass that's going to determine early start and early finish. And there's going to be a backwards pass that determines late start and late finish. Okay. Or if I were to express it, reflecting how it's actually computed, late start and late finish and then late start. So first pass, early start, early finish. Backwards pass, late finish, late start. Okay. And here we're going to define the overall project duration. The finish of the whole project is defined as the maximum of the early finishes for nodes. Okay. So we'll view the project as the earliest time that it can be complete is the time that's the last of the. So it's going to be viewed as complete if we're sure that we can complete any of the tasks within the project. So the maximum of the early finishes, the maximum of the latest time that's required given everything that has to be done. Okay. So we're going to go through a forwards pass, and we're going to go through a backwards pass. Now, what I want you to notice here, and this is the single biggest thing that trips students up in this area, is the nature of the relationship. In the forward pass, because all preceding activities must finish before a given activity can start. All preceding activities, all things that it depends on, must finish before a given activity can start. The start of a given node, the early start of a given node, is the maximum of the early finishes of the preceding nodes. It can't start until everything it depends on is finished. Okay? In the backwards pass, we have a different situation. So instead of dealing with a maximum of the early finishes, we're going to deal with minimum. And because preceding activities must finish before any following activity, the late finish of a given activity is the minimum of the late starts of the following activities. The last it could finish without delaying the project, it has to finish up before the late starts of all of the things that depend on it, or else it's going to delay the project. Okay, the minimum. Now, it turns out there's some intuition for this, so I want to go over this. But what I want to emphasize here is forwards pass uses maximum, backwards pass uses minimum. And there's a reason why. And you folks, I can almost guarantee, each and every one of you have applied this reasoning in the past. Okay? It's common sense at a certain level. And I hope that you can bring that common sense to bear on an understanding of this algorithm. Okay, so let's talk about the forward pass. Okay, it's 8 a.m. and you want to know what's the earliest time you can arrange to meet your teams after performance of tasks. So you want to take a shower, you want to boil some water, and suppose it's in a way that you don't have to worry about attending to it while it's boiling. You're going to have to eat breakfast, and you want to walk to campus. What's the earliest time that you can meet your team? This is the duration associated with these activities. What's the earliest time you could meet your team?
The total goes by a speed. Well, surely we can boil water while you're taking a shower. While you're taking a shower, there we go.
Eat breakfast, you're like boiling water.
Okay, so
you can walk to campus at the same time.
okay, that's a good question.
Can we eat breakfast while we take a shower?
the earliest time you could meet your team? 8:30. So give me the assumptions that go into 8:45. Okay, boil water, take a shower, and so you'll finish that by. Okay, why? Why by 8:10? Why not by 8:05? Because 8:10 is the maximum of those two times, right? You finish this by 8:05, and you finish this by 8:10, and you can't start breakfast until you finish both of them. So the earliest time that you can be ready for breakfast is 8:10. It's the maximum of those two times. Then maybe you eat breakfast, then you get up to 8:25, and then you walk to campus. It's 8:45. How about an earlier time? Can anyone do it if you could eat breakfast while walking to campus? Okay, depending what you're eating for breakfast, right?
Eggs, ham, toast, biscuits.
Yeah, you get pretty messy in some cases. Okay, the key question here, though, is what can be done in parallel with what, which is good. Okay, so let's think instead about the reasoning associated with this. So people brought out the key point there, which I was trying to make, which is you're dealing with a maximum of times. So now we're dealing with a different sort of situation. So suppose your plane leaves the airport at 8 p.m. You need to know what time you need to get up, what time you have to set your alarm. What's the latest you can set your alarm so as to make the plane? Let's ignore risk. Let's ignore risk that the cab may take longer than planned or what have you. So what's the earliest time that you have to get up? How do you go through this in your head? Okay, good. Okay, so let's do that. Okay, so here's 12 p.m. So you want to be at the plane 20 minutes before, so 11:40, right? You want to check in, so 11:20. You have to be there at check-in in case there's a line and so on. Okay, so it's 11:20. You want to be there, so you need to catch the cab at 11 o'clock, right? Okay. Now you have this issue with breakfast and waiting for the cab. So if I said 11 o'clock, okay, 10:45 you have to call and wait for the cab, and 10:30 therefore start breakfast and boil water 10 minutes, starting 10 minutes before that. What am I missing? Okay, good. Okay, so by when do I need to, what's the latest I can start to eat my breakfast? Oh God, I should have used it. Pardon me. I'm going to assume it takes 20 minutes to wait for the cab. Just to add texture to this. So by when do I have to start eating breakfast? Or by when? Yes. What's the latest I can eat breakfast? Start eating breakfast and still be safe. Okay. Okay. So in this case, what we're going to need to do is to reason about the minimum of the time associated with, okay, sort of the minimum of the start times of this guy and this guy is going to dictate by when I have to finish boiling water, right? So if I have to call and wait for the cab, say by, what would it be? Is it 11, 10, 20? Oh, okay, I've lost track now.
11 o'clock at cab to the airport.
Okay, 11 o'clock cab to the airport. This I have to do by 10:40, right? This I have to start by when? Well, if I have to do this, if I have to get in the cab to the airport by 11 o'clock, I have to call the cab by no later than 10:40. I have to eat breakfast. If I can do that while waiting for the cab, I have to do that by what? By 10:45, right? Right? And that means my water has to finish boiling by when? Sorry? take a shower by when? 10:40. 10:40. Exactly. Excuse me. This was 10:45, so this is 10:30 and then 10:25, right? Here we have to reason about basically what's the here boil water and eat breakfast are in sequence. You don't have to boil the water before you call the cab. So fundamentally, you have to reason out the minimum of this time and when you have to start to call the cab to take a shower. So let's go through this. So the question is, for what time you have to set the alarm? It's 10:15, but with that update, I have to check. So here's the algorithm. So the earliest event algorithm, you're going to be taking the maximum, the early starts of the predecessors, and the backwards algorithm, you're going to be taking the minimum of the late starts of the successors. Okay. So let's go through this. I'll go through this with an example. We'll put this on the board, and I'll draw this out. And I want you to walk through the reasoning with me, not just mechanically. Okay. So we have a diagram that looks like this. These are the inputs to the algorithm. What do those inputs consist of, please? What are the inputs to the CPM algorithm? Okay, list of tasks, the dependencies between them, but there's one other piece of information. Duration of those tasks, yeah.
I thought that was part of the task.
Well, yeah, you could define it as part of the test. That's fine. But if I ask you in an exam or pop quiz, it's not just the identity of the task, but their duration as well. Right? This is important. Okay, so we have this, and then we have this, and then we have two guys down here. So again, we're going to do early start, early finish, late start, late finish. This is duration. That's the task identity. And we have dependencies like this. Okay, so 2, 7, 2, 8, and then 4, 4. Okay, so let's run this algorithm going forward from here. We're going to assign this an early start time, the very first node, which we could always create if there's more than one. We're going to assign with early start time 0. Okay, so help me fill in the early finishes for this. So what's the earliest this node could finish? Yes. Okay. So the earliest it could finish, given everything that has to be done before it, which in this case is just that activity, is time 2. Okay. What about this one? What's the earliest this one could start? Day 2. Day 2. And what's the earliest it could finish? Okay, this is 7.
Oh, 7.
So what's the earliest it could finish? Good. Okay. So what's the earliest this guy could start? Okay. After all, it depends on this guy. This guy can't finish till 9, so the earliest this could possibly start is 9. Finish. Start.
11, 13.
Thank you.
Is that an 8?
That's a 13.
No, what's the one in the next node?
That's an 8.
Okay. So then we have 13.
Okay, so
Oh,
this
what?
is
Sorry, right. You may not get 13.
Why not?
We need to compute the other.
Because this might be what compared to that?
It could be higher.
Okay. Because this guy's not going to be able to start until both of these are finished.
Now we're changing the requirements. No, but it's different.
No.
Different example.
Why is it a different example?
Because you missed
Sorry?
No, 1, 2, 3, 4, 5. So the 5 on the top.
Okay.
But the last one is a 6, not an 8. Well, maybe we already.
Oh, okay, I misread it. Okay, well, we haven't taken that into account yet either. So.
Oh, okay.
gonna do this again.
Okay, so
This guy here.
9 and 13.
Okay. This guy why 9? Okay, good. 9 and 13. This guy. 13 and 17. Okay, now this guy.
17.
Okay. So how did you get that number?
The maximum of all nodes that enter into it.
This guy cannot start until both of these guys are finished, right? We can't start this guy until these ones are complete, and this one is the binding constraint, the 17, right? This is 17, what is this? 23, okay, good. Okay, now, we have the earliest possible time we could finish this project is 23, time 23. If we had stuck to this, adhered to this representation, there would have been an earliest possible time we could have started this that would then become the late start as well. The latest we could start it before finishing, and that's 23. So we're going to use that. So this is the latest we could start this task, finish this task without delaying the whole project unnecessarily. We can finish it by 23, and to avoid unnecessarily delaying the project, to avoid needlessly delaying things, we have to finish it by 23. So if we have to finish this by 23 to avoid needlessly delaying the project, by when do we have to start this? 17, good. Okay, so now we're going to work back. So for this guy down here, and I could have done either of these paths. Arbitrarily, I've chosen this one. So what's the latest we could finish this without delaying the project? Okay, and where did you get that number? Late start of this guy. Okay, so 17. And what's the latest we could start this without delaying the project? 13. 13. Okay. Okay, now, can we do this yet?
No.
Why?
Because it has a dependency. Another task depends on it.
Well, it has a dependency on this guy here.
No, that other task depends.
Well, okay, it depends whether you're talking the task dependency or the data dependency.
Oh, okay.
Okay, there's a data dependency here of this guy and this guy. There's a task dependency of this guy. Yeah. Okay, so let's go this way. So what's the latest this could start or could finish without delaying the whole project? Okay. What's the latest it could start without delaying the whole project? Okay. Yeah. Okay. Okay, now, this guy. This is not a B, this is a 13. So what is the latest this guy could finish without delaying the whole project? Okay. Why not 13?
Because of the other dependency.
Because this guy then wouldn't be able to start in time, right? Okay, so this has to finish by 19. That is the minimum of those two. Remember we did maximum over here earlier. Took the maximum, this guy was associated with the maximum of these two. This is the minimum. These two are coming together here, but it's going to be the minimum because we're not going to be able to finish the project on time unless this guy can finish by a time required by any one of these guys. We can't finish this later than the latest start time of any of, the earliest start time of any of those guys. The earliest late start time of any of those guys. Okay, so this is 9, so therefore this is 2. This is 2, therefore this is, okay.
No, it's 0.
The exponent of negative infinity. If you log transform it, it's negative infinity. Okay, so what is this telling us? This is an exercise we've just gone through, and at this point these are just numbers. But why are they interesting? What? Okay, yes, there exists slack on the above path. So you'll notice that the earliest start time of this node and the earliest finish time, or the latest start time are different. We have latitude as to when we are going to start this task. We could start it as late as 13 and still finish the whole project in time. Similarly with this guy, right? We have some choice. We have some wiggle room, as it were, as to when we are going to start this project. We can start it as late as 15. Well, we could start as early as 11, but we have the latitude, we have the freedom to start as late as 15 and still not delay the whole project. That's important. Ladies and gentlemen, what here is the critical path? What's the path you have to keep your eye on? What's the path that...
The lower.
Okay, it's this one here. So if we were to draw the critical path, be this guy here, going up through those nodes. That's the one that really matters as far as constraining how quickly we get things done. Let's put it this way. A delay of a single day on this lower path will delay the project, the whole project. A delay of a single day on these nodes here, will they delay the project? No. We have this float there. We have slack. We have latitude. We have wiggle room. You can put it in any number of different ways. There's a different example here for you to, well, actually, no, it's not. It's going to come up to the same thing. Okay, so this notion of slack or float measures leeway in scheduling. It's the degree of freedom that we have for scheduling. And it's the length difference. It's the difference between, not length of difference, length of time, or difference between when we have to finish a given task and to avoid delaying the schedule, and what's the earliest possible time. And in this context, if you're dealing with software that's available these days and you have, for example, start-to-start dependencies, it can be defined in different ways in those contexts. But here we have it defined, we can compute it either with late finish minus early finish, or late start minus early start. It's going to be the same for both of those. When you have those different types of dependencies, it's different. And the key understanding here is this activity might not be a bottleneck. It might not be on the critical path. While it may be possible to schedule activity at many different points, it may be notable that some of those may be far preferable to another. So if we have resource dependencies, it may be desirable to schedule these things either earlier or later so that we don't overload our resources. Our resources aren't too long. So this gives this notion of critical path, and the critical path is the longest zero float path. Now, it turns out if you're dealing with these more sophisticated types of dependencies like start-to-start, etc., the notion of the critical path has some non-intuitive features. Here it's completely straightforward. It's the longest zero float path from start to finish, and it must be completed on time or the entire project is delayed. It determines the minimum time for the project. Here, this path was what determined the 17 and the 23 here. We took the maximum of this 13 and this 17, this path, sorry. Critical path is this one. So this is the path that determined the 17. It determines the minimum time that's in which we finish the entire schedule. Now, the critical path typically evolves over time. Why would it evolve? Why do I say it evolves over time? Yes, as requirements change, that's true, which may introduce certain types of dependencies, etc., new tasks. But there's another reason it evolves too. What's another reason this critical path might evolve as this project falls into place? Yeah. It's possible that you've scheduled 2 for this, and instead it takes 8. And suddenly the critical path is where? The top.
Oh, is that what the last clause?
You mean
No, like on
in the diagram?
top.
Oh, this guy here?
Yes.
No, this is just typically where it puts the name of the
Oh, I
or
see.
the ID of it. This is just one convention, though. In any case, you do within software typically keep track of how long things actually take, and it can shift the critical path. It can shift the path from one point to another. So you got to be a little bit careful about that risk of shifting. However, so if you delay this too much, it may shift the critical path up here. On the other hand, this is the one that you know that a delay there could be really problematic in terms of delaying the whole project. So this will help you prioritize your attention to products. It's quite common that you might, for example, create contingency buffers, some amount of slack deliberately at certain points within your project to accommodate some of these dependencies. There's a technique known as precedence diagram method, which is actually more popular than pure CPM these days, which extends to multiple relationships, and you can have what are called lags within that. So you can represent delays associated with, say, finishing a previous one and starting a new one. Here, those lags or lead times can add extra degrees of complication. You don't have to worry about those. An earlier version of this class, I used to talk about several notions of float. The most common one by far is total float. I do want to distinguish these a little bit. There's three fairly common ones. The most common one of all, though, by far, is total float. This is the maximum time an activity can be delayed without delaying the finish date of the whole project. Okay? So the float here associated with given activity is simple to compute in this simplified version of these methods, this sort of pure CPM. Here you just subtract the early start from the early finish, or the late start from the late finish. You take your pick. But it's going to yield the same difference either way, because this guy is just these plus this value. So you compute the difference. This has a float of a total float of 4 associated with it. Okay, that's described there. Free float, by context, is the maximum time you can delay without delaying any of the successors. The issue here is that, particularly in some domains such as engineering and construction, it can be contentious, this whole issue of total float. The problem is that if different parts of a project are being done by different people, say by different contractors, suppose I'm on a part of the project which has float, and suppose I eat the float. That may suddenly mean that someone downstream is now on the critical path it wouldn't have been. And that can impose risks on them, risks of lawsuits if they slip up. They would have had latitude, they would have had slack, they would have had degree of freedom or wiggle room as to when they can do the project, but now they don't because of my actions. So in other words, if I'm associated with this task and I end up dawdling or end up attending to some other project entirely, and then I come back to this on day 13 and start delivering, suddenly this person here has got to deliver right on time. So there's a notion of free float, which is the max time you can delay a given task without delaying any of its successors. Okay? And it turns out this is sometimes is different, typically is different from the total float. And I think I have a slide in here which shows an example of this that I don't want to go into because of the time. But free float is a stronger notion of float. And you can burn your free float without affecting anyone. For example, you might be able to burn your free float here. This guy has free float, equal to 4. It has total float equal to 4. This guy here has total float equal to 4, but 0 free float. If this guy delays by, say, 4 days, or by 1 day, it's eaten the slack of this one. It's eaten the float of this one. Now this one has less flexibility about when they schedule things. I've imposed a hardship. I've imposed tighter constraints on the later person. By contrast, this task here, it can delay by a day, and it's not going to delay this by a day. There's no one that's going to be directly harmed. So this one actually has 4 free float and 4 total float. By contrast, this guy here has 4 total float, 0 free float. Okay. Anyway, there's an example in there which illustrates this. And then there's a more sophisticated notion of independent float. These turn out to be surprisingly important when there's litigation involved. Because one of the ways that litigation takes place is, sure, it may be that my delay caused this mall to not be able to open until after Christmas, and therefore they missed the Christmas season, and therefore they sue me because I'm a contractor that didn't deliver in time. But if I can show that my delay or my inability to absorb that delay without cost was due to somebody else, to another contractor, then it may be that they're the one ultimately liable. So these issues of float come into play in that context, and here's the element. So I want to emphasize here in closing a few elements that I will absolutely hold you responsible for this lecture. Number 1 is critical path. Number 2 is total float. I'd like you to know free float, and that's a second order one, but it is potentially testable. And I'd like you to have intimate capacity to run the CPM algorithm. You should know what its inputs are, identity of tasks, duration of tasks, dependency. And you should be able to run its forward and backward paths and compute in this sort of way. You should also know something about the importance of dependencies, and particularly how they can be valuable in the case of changes. By representing these dependencies, I can compute a new schedule when it turns out, for example, maybe this guy took 4 days instead of 2. I can compute a new schedule accordingly. In this case, it won't cost much. Or if it took 6 sick days instead of 2, then it would become part of the critical path. Okay, I think that's all we'll go through today. I want to emphasize the CPM algorithm is very cheap. You can do it in order n time. This is theta n time, so it's actually tight. It's not just an upper bound, it's also a lower bound, how quickly it can be done. And you will find, those of you who are in a project management capacity or are going to be involved in scheduling, you'll find no shortage of tools online which will allow you to do simple scheduling of this sort. It would be my hope, given the incremental nature of the deliverables here, that probably you'd have a few enough activities that you could even do this by hand if you wanted to do so. Few enough tasks per milestone. But I would like to see project schedules. I would like you to do so with rather granular tasks. They don't have to be very, very small tasks. But you should be thinking about where's the critical path for each deliverable. What are the things that we have to hit in time to finish this thing as quickly as we can? Where that final constraint is not so much the formal deadline of it, but how quickly we could do the other tasks, okay, just like it is here. We could do this, so we could finish this by time 23, and that imposes the constraints here. Okay, so those are all the comments I have for today. Any questions right now? Okay, so I'm going to leave the teams to meet. I think team 1, if I'm not mistaken, wanted to meet with me right now. So on page